Well, good evening, everybody. My name is Charles Schultz, and this is the Randomizer, and we're going to look at an interesting term tonight. Another one was pulled out of the hat, and this one is Snell's law. And a lot of people don't know much about optics. They see things working around them with lenses, mirrors, and liquids, and they see odd effects every now and then. And sometimes we simply accept them for what they are. But it's only when they're formalized that we get to turn them into interesting tools. And Snell's law is one of those examples of taking a simple phenomenon and finding a mathematical model for it and having great influence in science and industry and many other fields. So we're going to talk about Snell's law and its long and twisted history for a couple of thousand years. And Snell's law is going to bring us some very interesting things to talk about. Some things you can actually duplicate very easily at home in terms of experiments, and some of them are rather fascinating to watch. I'm going to encourage everybody to go to universesciencecenter.com or schultzlaboratories.com. Click through to our pages, walk in our galleries, put on your Oculus if you've got one, and just navigate around, have fun, and work in a 3D environment. And we also encourage anybody who has expertise to share it with us and the world at large by getting a gallery or teaching center put together in our virtual world, and you can use it as your classroom. Every weekday, 6 p.m. Eastern Standard Time, we have the Randomizer with a new random technical term, and we encourage everybody to join us, bring your questions, your ideas, and your thoughts, and join us live during the show, and we'll answer your questions best as we can. So let's get on to Snell's law and figure out what it's all about. Now, I know a lot of you have aquaria, and when you look in the water, you'll notice that if you were to put a stick or something in the water, it would appear to bend at the surface of the water. And you're wondering what causes that effect. And if you stand in a swimming pool and you put your arm in the water, it appears bent in the water. And it's a simple thing. We've seen it and in many different ways, but we often wonder what causes that to happen. Well, the real simple answer is refractive index. And what this is we know that when light travels through the vacuum, it travels unimpeded and there's nothing to slow it down, so it works at its top speed of light. And also in air, it is such a thin medium that the light does not easily bend or distort or slow down in air. Although, when air is hot and cold in different areas, you can see the stars twinkle at night due to refraction, because air that is hot has less density and cold has higher density, and it acts like a random lens and twinkles the stars. It breaks up the beam of light. So air does have some optical properties, but the speed of light is a constant. So how can it be different when it runs through something like, say, water or oil? Well, the fact is, light traveling through a vacuum doesn't encounter any obstacles. But when light travels through a liquid such as water, something very, very different happens. The photons of light traveling through space reach your eyes unimpeded. They're probably the very same photon that was emitted by the star or the planet or the moon you were looking at. But if you're looking through water, there's an entirely different process. If you measure the speed of light in water, it appears to be substantially slower than in a vacuum. And this is called refractive index. It's the ratio of the time in vacuum divided by, well, the time in water over vacuum, for instance. And if you measure the refractive index of water, it gives you an answer of about 1.33. And if you measured the time it takes to go through oil or Pyrex glass, the answer would be like 1.47, almost 1.5 times slower than through a vacuum. So how does light move more slowly? Actually, it doesn't. The trick is, when a photon of light strikes matter, it is absorbed by an electron in that matter. And that electron might go around the atom a few times, and then at some point it's got to re-emit it if it's something that's transparent, such as water or glass. When it does, it travels at the speed of light until it encounters another electron, and then it's absorbed for a moment and it dwells, and then it's re-emitted. Now it goes in the same direction because of the conservation of momentum. It can't change direction without an outside influence. So that's kind of interesting. But what we're seeing is the speed of light did not change, But all the times it was absorbed and re-emitted, it had to dwell there for a short period of time, a few trillionths of a second perhaps, and then be emitted, and then it does it again. So it's stop and go, and every time it's moving at the speed of light, but the sums of all the stops along the way add time of passage. This is what slows down the light passing through a medium, and this is the source of refractive index. So if you measured the speed of light in water, it'd be about 75% of what it would be in a vacuum. Thus, it takes 133% of the travel time. And if you measured it in oil or Pyrex, it would move about 68% of the speed of light in vacuum. And so therefore, it takes about 147% of the time to travel through that medium. So this is the root of it all. Now, how do we describe that, and why is it important? Well, it turns out that lenses are made of glass, usually, and that glass has an index of refraction. And different types of glass will have a different index of refraction. So what is refraction? It basically is to bend or curve the beam of light. And we measure it from the surface itself. So if you have a surface of glass and you have light through the air and then it strikes that surface, two interesting things happen. One, at the angle that the light strikes the surface of the glass, it will reflect at a mirror angle part of that light. And so those two angles around the vertical are exactly the same. That is the angle of reflection. But when it enters the glass, it changes to a narrower angle. And that angle is determined by the index of refraction. And there it travels at a different speed, slower, but at a different path as well. And it's because of that conservation of momentum. It can't get energy for free, and it's not going to simply give it away. And so the light follows a different path. When it emerges from the other side, it takes off at the same original angle. Now, Snell was one of the people who studied this phenomenon and decided to make a mathematical treatment of it. Well, this actually went all the way back to Ptolemy, who was a mathematician and an astronomer, and he was in Alexandria, Egypt. And Ptolemy lived from the year 100 to the year 170, roughly. We don't have exact numbers, I don't think, on that, but that's pretty close. And one of the things he did was he came up with an estimation, an estimation of this rule, but it was rather inaccurate. And, honestly, he kind of fudged his numbers a little to make it look better. But the larger the angle was, the worse the answer got. Nevertheless, it was the first stab at making a rule about refraction. A little after that, there was an Arabic mathematician named Alhazen. And Alhazen, around, he wrote a book called The Book of Optics that was published in the year 1021. And he described the rule a little more accurately, and he didn't fudge his numbers. And so what he did, he wrote a book about mathematics and geometry, and actually he was the person who became the first to try and create a link between algebra and geometry. So he was a very prominent Arabic mathematician of the day, 1,000 years ago. But in his book, he did at least have a pretty accurate description of the rule. Now, this eventually became named the Snell's law, because Snell was the first one to accurately describe it. And, the first person to accurately describe it, to be honest, was Ibn Saul, who was in Baghdad, in the court of Baghdad, in the year 984. And the manuscript he wrote was Burning Mirrors and Lenses. Now, this is interesting. He formulated a version of the law that was accurate enough for him to create reflective mirrors that could focus an image with no geometric distortion of any, appreciable amount. They were using the technology of the day. But this is notable because even at the time, they would use mirrors, curved mirrors that were silvered as reflecting surfaces for optical experiments and optical purposes. And they could cast a beam of sunlight at a remote point and focus it and create a fire. We've heard that from history before. So this actually was the first practical application of this rule to create accurate lenses and reflecting mirrors that could cast an error-corrected image or an error-free image. Now, it was rediscovered by Thomas Harriot in 1602, but he didn't publish his results, although he corresponded with Kepler, the man who we know about orbital periods in astronomy, on this subject in 1621 now. The Dutch astronomer Willebrord Snellius, who we also know as Snell, came up with an actual formulation of the law. And in his law, what he found was that the incident angles multiplied by the sine of the angle gave a value that would equal the refraction angle times its sine. So he came up with a relationship that matched the material using trigonometry. And it was an extremely accurate one. In fact, it actually became very important in technical optics in the early 1900s. And in 1962, it was seen in work with optics and telescopes and other systems. So we'll talk a little about that in just a moment. But Snell's law turns out to be very simple, but it required an understanding of trigonometry to formulate it properly. So what's most interesting about it is we now understand that if you have a material with a certain index of refraction, and it's placed in a medium that has a different index of refraction, you can see the material even though it's transparent. And you can see a piece of glass, such as a drinking glass, in quite good detail because the surface refracts and reflects the light in a very characteristic manner. There was a company not long ago that actually made optical coatings that would verge in on the refractive index to try and match the two. And they made small glass artifacts that were literally almost invisible by matching the index of refraction, the transition zone at the surface. Now, these invisible optics devices were kind of a curiosity at the time, but some of them have found some practical applications in certain technologies. If you want to do the same thing, you have a Pyrex beaker or measuring cup, and you pour vegetable oil in it and submerge another Pyrex piece inside the oil, it will become invisible because the refractive index of the glass and the oil are almost exactly the same. So you've literally made the transition zone for light traveling through the oil and through the Pyrex go away, and therefore it becomes invisible. All the distortions of the optics of the glass and the oil perfectly counter each other. So this is the way to make some glass items vanish. I've seen other things done the same way. Certain solvents, certain clear materials can be placed in a beaker, you pour it in, and it vanishes. It's a neat trick, and you can duplicate that at home very easily. There is a way to make a solution that has a varying refractive index. If you have a laser pointer, and you have a small rectangular box that's clear, it could be an aquarium, and you fill it with a solution of sugar and water. And the sugar gradient is denser at the bottom and thinner at the top. There's a grade of density of sugar dissolved in the water. When you shine the laser beam through, as it increasingly hits more and more refraction, the beam of light will literally curve inside the liquid. This has actually been used, in a sense, to make gradient optic components that bend the beam of light at varying angles depending on where the beam enters the optical element. So we can play some pretty cute tricks with optics and Snell's law and varying the density or refractive index of certain optical materials. So this is a long, I'll tell you, there were so many things to know about the history of this. I copied down some notes because I'm telling you, I have a great memory, but sometimes I want to be absolutely sure I'm saying the right things. And understand that there were many people who got involved in this controversy. There was a mathematician and philosopher, and we know him by René Descartes. Descartes actually worked on the problem of refractive index for a while and came up with a solution that was very, very close to Snell's law, to the point where people accused him of actually copying the work. We know now that that actually wasn't true. But one of the things that stands out in my mind from this is this. When we talk about the laws of physics and optics and electronics, these are things that are written into the fabric of nature. And it doesn't matter who you are, where you live in the universe, what planet you're on, doesn't matter. When you start investigating these things and you start making measurements and recording your data, and you discover the underlying principle, it's going to be exactly the same no matter where in the universe you are. And so one of the cutest things about this concept, one of the most attractive things about this concept, is that anyone in the universe can make a discovery in math or physics, and it will be exactly the same as a discovery somebody else on some other planet made at some time. Because the way I see it, the universe is a message and we are its interpreters. So you're going to get the same results. And it's not uncommon for numerous people, scientists, physicists, mathematicians, to make the same discovery in varying times throughout history and in varying places in the world and getting the same results. Simultaneous discovery is not unusual when there is a growth of technology and information and understanding. So it isn't that somebody saw something and then copied it and ran away. Ha ha, I got it now. That's not the point. The point is a discovery is a discovery. And if you're correct, you're discovering one of the laws of nature. It's not a matter of copying. It's a matter of understanding and interpreting. Some people feel that they are the receivers for some cosmic message or principle. And I guess that's an artistic way of describing it. But the fact is, if you're smart enough to figure out how something works and you write it down and you publish it, it's quite possible that somebody else has already discovered it or already published it or will, and there could be a conflict. Doesn't have to be a conflict. You found a piece of nature. And Snell's laws was definitely one of those things that got bandied around for around 2,000 years before it all was understood and put into full practice. So that's pretty much what I have to say about Snell's law. And I think if you have an interest in optics, it would be worth looking up some of the history. Wikipedia has a number of great articles on it. Britannica Online has a few as well. And just look up these philosophers and their thoughts on optics, and you can see how their thinking proceeded. It's a pretty interesting thing to kind of do an autopsy on, how the ideas came together, what the influences are, and how they arrived at the same conclusions. And it's pretty informative overall. So I hope that you find a little something that tweaks your imagination or your interest there. And meanwhile, I'm going to open the floor to questions and comments, and I am going to encourage you to become a member of Schultz Laboratories or Universe Science Center. Come to our galleries and explore them and set a classroom up with us and share this with your friends, get them interested. And if you're doing a homeschooling effort or you're training somebody for a company you work with, contact us. We'll set up a specialty gallery so your employees can sit down in there, move around in virtual space, and learn to operate a machine or learn a certain principle or whatever you want to do. It's a great way of training. It's interesting. It's engaging. So that being said, join us every 6 p.m. weekdays for Eastern Standard Time. I got to be careful about that, for the randomizer, and we'll pull another technical term out of the hat and talk about it. And meanwhile, I see a question. Radiation related to speed change in radiation. I'm not familiar with that one term, I have to admit. Let me open my chat box here. Rakovich radiation, related to speed change in radiation. I don't know. I do know that Cherenkov radiation, which may be related, when a material radiates a photon or a particle, and it moves faster than the speed of light for a given medium, then you get blue-white radiation given off as well, Cherenkov. Okay, very good. Yes, that was the term. Okay, in many reactors, you will see a bluish glow around, let's say, spent fuel cores down in a pond of cooling water. And what's happening is the particles are being radiated at greater than the speed of light for the water. And as a result, secondary emissions are happening, and it looks like a blue-violet glow or soft blue glow. That is actually caused by breaking the speed of light barrier in water or in oil or in glass. That is exactly it. So yes, if you try to exceed the speed of light in a medium, it'll definitely take that photon apart, and it'll spit out a glow called Cherenkov radiation. So yes, that's absolutely exactly what it is. And thank you for the question, Jim. Okay, and anybody else with any questions?
Yes, I have one. This is Elizabeth.
Okay, go right ahead.
Hi. Was Ptolemy, when you said he was sort of fudging the numbers to
Yep.
make refraction theory work for himself in that period of time, was that mean he was compromising as a...
Well, okay, that's an excellent question. Was Ptolemy compromising on his figures? Now, some would be generous and they would say, well, maybe he was worried about the accuracy of his numbers and just kind of cleaning up the data a little. I'm going to say something. I wasn't there. I didn't see what he did. I only have the historical records. So I couldn't really say, although it's certainly a possibility. I know that many times when you have an answer that almost looks right, and you try to draw a line through the scattered numbers that you've got and make a nice clear answer out of it. Some people would be calling that, averaging your data to clean it up. Some people would call it fudging the numbers. And I think that really his desire to find the answer might have overridden his common sense. That's a possibility. I really know nothing about the man's character other than the fact that he's a heck of a lot more famous than I am. So, what I will say is that it's not often, if you have poor instrumentation, that you will get not very accurate readings and you do the best you can to get the most reasonable answer out of it you can. But it certainly is true that he did do the experiments and he did make an effort to get an answer. And from a charitable standpoint, I'll say, he was a good scientist in the fact that he did a lot of science and he did a lot of readings. So I hope that answers the question, respectfully and realistically. I don't know what sort of optics I would be able to put together in the year 100 AD. Well, all of that said, are there any other questions?
Thank you.
You are very welcome. Well, then, at that point, I'm going to read my quote for the day, and we're going to wrap this up. And Jesus led them out as far as Bethany, and he lifted up his hands and blessed them. Now it came to pass, while he blessed them, that he was parted from them and carried up into heaven. That was Luke 24:50 and 51. And what an amazing statement. I love these quotes, and it makes you think of things from a different perspective. I see a lot of people take exception to reading quotes from the Bible, and I point out that somebody 2,000 years ago knew what we were going to be going through right now, and if that isn't a sign of having some answers a couple of millennia in advance, I don't know what is. I'm always amazed by some of the things that I do read there. Well, at this point, we've dispensed a little information on Snell's law, and I hope some things to make you think, and a couple of questions. I always appreciate that, little interaction. And it's just going to be a wonderful weekend coming up here. Today, what, Thursday? Enjoy the randomizer. I always do, and I love putting this together, and thank you for everybody who participates. And do become a member, help support our efforts. And I hope that I will see all of you tomorrow at 6 p.m. with a new randomizer term. In the meanwhile, have a wonderful evening, and as I always say, make the world a better place. Thank you. I'm Charles Schultz.